तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. In the last two lectures, we had introduced two topics. One was the electrostatic potential and the other was the divergence theorem. So, this lecture what we will do is use these ideas in some problems and finally lead up to Poisson's equation. So, let us do some review. We had started with a very important idea in electrostatics that we derived. We showed that if you took the electric field and worked out this integral E dot dl going from any point r naught to a point r in some path. So, if you did this integral r naught to r, the value of this integral depended only on, is a function only of the endpoints. It depended on the value of r, it depended on the value of r naught, but it did not depend on how you went from r naught to r. You could have gone this way, you could have gone this way, you would have got the same answer. Since the answer did not depend on how we went, the answer must clearly be a function of the positions r and r naught, and so we identified a scalar function, because this was a scalar, vector dot a vector, so it is a scalar, the integral of a scalar is a scalar, so it is a scalar function and we gave it a name, electrostatic potential phi, and it has a value at every point in space, and when I do an integral from r naught to r, the answer I get is the difference between the value of this potential at r and the value of this potential at r naught. So, we have derived this, and as I told you, it is something very important about electrostatics that you are able to do this. Now, another equally important thing that we found out was that you could relate electric field and potential, namely you had a relation that the electric field was got by taking this scalar field phi and applying the gradient operator to phi. E was equal to minus gradient of phi. The way we showed this was to say the following: I have a point r, the electrostatic potential at this point is got by going from some reference location through some path to r. Now, if you look at some point near r, a point I will call r plus delta r, the potential at that point comes by doing this integral from the same reference point on another path up to this point r plus delta r. Now, it could be any path at all. but as we discussed last time, I will choose a specific path. To get to this point r plus delta r, I will follow the same path up to r and then go in a straight line from r to r plus delta r. So, I have potential at r plus delta r, that is this value, is equal to integral up to r of E dot dl, that is this first part, plus integral r to r plus delta r of E dot dl. But this is nothing but phi of r. So, I get an equation which says phi of r plus delta r minus phi of r is equal to integral r to r plus delta r E dot dl. Now, as we discussed last time, since this is a very short distance and it is on a straight line, you can say that this is equal to E dot delta r. And when you study the properties of phi, it is easily possible to show that this implies the electric field is equal to, well, there is a minus sign that I have missed, this is minus of. So, it is minus E dot dr delta r, E is equal to minus gradient of phi. So, there are two very interesting relations between electric field and potential. First, I have that electric field, and once again there should be a minus sign here, please note. The electric field integrated from one point to another gives me the potential, and if I take the potential and apply the gradient to it, I get back the electric field. So, in other words, from the electric field I can go to potential, this is by integral E dot dl, and from the potential I can go back to the electric field, this is by gradient of phi. All right. So, that was one concept that we have, I think, looked at quite thoroughly. Now, the second concept we looked at last lecture was the idea of electric flux. And the idea here is that when you have a charge, group of charges in fact, you have an electric field that develops, and at any point the electric field that points has a direction and a magnitude, is equal to the force exerted on a charge divided by the charge itself, because F is equal to QE. But there is another way of looking at electric field, and the other way of looking at electric field is, let us assume that from every charge some electric field lines leave. You have many charges, and from every charge some electric field lines leave. How many electric field lines? As many as the magnitude of the charge. If this charge is 1 unit, maybe 8 electric lines leave it. This charge is 2 units, 16 electric lines leave it. These electric lines, because the electric field has general shape, the electric field changes direction. The line that joins all these electric fields is called a line of force. I haven't proven it, but you can show that lines of force are a very good concept, that in fact it is not just for drawing. And another way of talking about the strength of the electric field is to count the number of lines of force that cut through unit surface area at a point. So, electric field is F over Q, but it is also equal to number of lines of force per unit area. Now, we used this idea last lecture. We said that supposing you have a volume, I am going to call it S, and supposing I have lines of force, and this line of force cuts through this surface at some point. So, the electric field is in the direction of the line of force, whereas at that point the line of force has a normal pointing some other direction. If you want to count how many lines of force go through the area ds, we worked it out last time, it is equal to E dot ds. So, this is a little bit of flux that cuts through this area ds. So, we can integrate this number over the entire surface. So, we can construct a surface integral, and this circle means over the entire surface of E dot ds. This is equal to total flux, electric flux through surface. And we worked out last time that this E dot ds for a single charge, if the electric field is due to a single charge, is equal to 0 if Q is in V and is equal to, sorry, is not in V, is equal to Q over epsilon naught if Q is in V. So, it is a binary kind of relationship. If the charge is outside, there is no net flux. If the charge is inside, there is net flux. If you put two charges, then this applies to each of the charges separately because we have superposition. So, we can actually talk about n charges, some of the charges inside the volume, some of the charges outside. Then when we do E dot ds, this will apply in turn to the electric field due to each of these charges, but only those charges that are inside the volume will give me flux. The charges that lie outside the volume give me 0. So, actually we get a result which says surface integral E dot ds due to many charges is equal to charge enclosed by volume. So, this is a surface and this is the volume enclosed by the surface divided by epsilon naught, and this is called Gauss's law. Now, there is only one more step, which is that I can do some mathematics on this surface. We showed that you can write this surface integral as a volume integral over the same volume, divergence of E dV. We showed last time that these are saying the same thing. And what is charge enclosed by Vs? It is nothing but the volume integral over the same volume Vs of charge density rho dV. I can combine the two volumes, and so I get a single volume integral Vs divergence of E minus rho over epsilon naught dV is equal to 0. Now, this by itself does not tell us anything. I mean, it is a volume integral of a function is 0, that can happen to many functions, but it is saying much more than that. It is saying that the volume integral of this quantity is 0 for any volume, because we did not specify what this volume was. It is true for each and every volume, which means I can take a microscopic volume about any point r. So, I can take a volume just around that point, which means that this volume integral will become divergence E at that point r minus rho of r over epsilon naught times delta V is equal to 0. Delta V is not 0, so it must be that this bracket is 0, which means divergence E is equal to rho over epsilon for all r. This is known as the divergence theorem. It is equivalent to Gauss's law. There is nothing that one has that the other does not have, because we use Gauss's law to derive this, and if you knew this, this must obviously hold, because if this holds at every point, the volume integral holds at every point for any volume as well. So, it is these two ideas that we are going to use this lecture and eventually derive Poisson's equation. The first example I am going to take is going to be a cable. I have two cylinders, the inner cylinder has say a radius A, outer cylinder has radius B. The region between the cylinders is empty, it is air. So, in this region we have air. The cylinders themselves are made of metal. And what I have done is I have put some charge on the inner cylinder. The amount of charge I have put is q coulombs per meter. And the question is, I want to obtain the electric field and potential in A less than R less than B, that is in the region between the two cylinders. So, if we look from above, then the same picture looks as follows. I have got two circles. The inner circle has a radius A, outer circle has a radius B. On the inner circle is some charge, the charge is q, it is q coulombs per meter. Now, let us look at a third cylinder, which I am drawing with a dotted line at some radius r. Now, if I look at this cylinder, due to the symmetry of the problem, I know that the electric field is going to point away from q. So, on this cylinder, this electric field is going to point radially away. So, if I want to compute a relationship between electric field and charge, what I do is I construct the following box. The box has a height h, it has a radius r, and it encloses a height h of the inner cylinder. Now, the electric field is radially outwards. So, it means it is tangential on the top surface and it is tangential on the bottom surface. So, it means that if I want to do surface integral E dot ds, there is no contribution from the top surface and the bottom surface, because the electric field is neither entering nor leaving, and this integral is about electric flux that is passing through the surface. So, there is zero contribution from the top and bottom, there is only contribution from the side. So, it becomes E sub r, the radial component of E, which is a function of r, multiplied by the area. Well, the area is 2 pi r h. Now, this surface integral E dot ds is equal to the enclosed charge. How much charge is enclosed? It is equal to the volume integral rho dV, or in this case, since I am given q, it is equal to q times h. That is, it is q coulombs per meter, this is a height h, so it is qh coulombs per inside the box. So, I now have a relation between electric field and charge, that is 2 pi r E r is equal to, sorry, this is qh over epsilon naught. So, solving this, I get the electric field. The electric field, which is in the radial direction, is equal to the charge per meter times 2 pi r epsilon naught. So, if I plot this, this is the radius, so the radial distance. My inner cylinder reaches here, so this is A, my outer cylinder is here, so that is B. What I have is that the electric field looks like 1 over r. So, this is E r. Now, what is E r inside the cylinder? If this is a solid, if the inner cylinder is a solid metallic piece, what is E r inside? Well, to answer that, we take the same approach, except we try to put the cylinder, this dotted cylinder, entirely inside the inner metallic block. So, how would that work? I have radius A cylinder, and within that cylinder I put this imaginary surface. So, again I would get surface integral E dot ds is equal to q enclosed divided by epsilon naught. Now, the question is, what is the surface integral? Now, I am sure you have learnt all this in school, but it never hurts to relearn certain things. So, let me go through the argument. Now, any metal or semiconductor or any conducting medium consists of charges that move, and in the kind of materials we are thinking of, you have charges which are usually electrons, and in the presence of an electric field, let us say in this direction, what happens is that electron feels a force. The force it feels is in exact opposite direction, because the electronic charge is actually minus. All right. Now, this electron therefore starts moving, it starts speeding up, and if you plot its velocity in time, velocity of the electron, well, it will start decreasing. Let us say it started at 0 and it starts decreasing, but in no time at all this electron is going to bang into another electron or into a atom, at which point the electron forgets all about its earlier velocity and goes to a new velocity. It may be positive, it may be more negative, it may be 0. Then it starts accelerating again, has another bang, accelerates again, has a bang, and so on and so forth. Now, in the process of doing this, the electron develops an average velocity. Now, the average velocity of the electron is obtained by writing the force equation. And the force equation for an electron would be mass of the electron dV dt, that is d dt of the velocity. So, this is the rate of change of momentum, and Newton told us this is equal to the applied force. But what are the applied forces? Well, there is minus E times the electric field. That is an applied force. We do not have a magnetic field in this problem. We will ignore the gravitational field, but there is one more force that is present. It is the force of collisions. Now, you can see that this is a kind of instantaneous force that acts at very short period of time every now and then, but that is very hard to model. So, what we do is we define it as a friction minus m nu v. This is the mass of the electron times a collision frequency or a friction factor times the velocity. The idea is that if an electron is here and it is moving with a certain velocity v, it will interact with other electrons and atoms. It will interact with them provided they are within range. So, let us say that the range over which it can interact is some L. So, you can draw a cylinder. The cylinder has a radius L, it has a length equal to V t. V is the velocity, t is the time. So, that is the distance that the electron moves if it moves at constant velocity. Now, if it meets up with another electron in here or another atom in here, it is going to collide. So, the faster it moves, the more space it covers, more likely it is to collide. So, that is why the V is there. The more electrons there are per cubic meter, the more tightly packed the electrons are, the more likely they are to collide. That is this collision factor. And when it does collide, there is a change in velocity, and the amount of momentum that changes is proportional to the mass of the electron. So, that is where this term comes from, m nu v. Now, if you take this and you believe it, and I can tell you that it is an approximation. There are plenty of situations where it is not true, but it is true inside a metal. It is more or less true inside metals and semiconductors. Now, if you take this and you say, I will wait for steady state, then this piece goes away. Again this is fake, I am cheating, because that diagram I drew showed you the electron velocity jumping up and down. So actually what I have to do is I have to average this equation over a fairly long time. Then what will happen is the electron velocity goes up, comes down, goes up, comes down, on average it does not change, and so the dV dt term goes away. So we are talking about average velocities and average electric fields. The way to denote averages is to put angle brackets around them. So what do I get? I get that the average velocity of the electron is equal to minus E over me times the average electric field over nu. So I now know that the electron drifts, and it drifts at a speed that is proportional to the applied electric field. It is also proportional to the charge over mass, and it is inversely proportional to how many electrons there are present. The larger the number of electrons, the more they slow it down. So you can't have much drift velocity. Now when you ask what is current, current is basically moving electrons. So if I have a wire with a radius a, and if the wire has n naught electrons per meter cubed, then the current that flows will have to be pi a squared times this V bar. This is the volume swept out in 1 second times n naught. Why do I say that? I say that because supposing I am watching here and I count electrons for 1 second. Okay. Well, how many electrons will come? I will have to multiply the space, the cylinder that swept out, times the number density of electrons. So this will be V bar, and this will be the area, pi a squared, and of course I must multiply by the charge of the electron. So what it means is that ultimately the current is proportional to the velocity is proportional to the electric field. If I have an electric field present, there is going to be average drift of electrons, and that is going to result in a current. Where does this take us? Let us go back to the wire or the metallic object. I am supposed to have a radial electric field because it is symmetric. So if I have my imaginary cylinder and I said I have radial electric field everywhere, what it means is there is current flowing out continuously. So for the next, as long as we wait and watch, maybe 0.1 coulombs are going to flow out per second from the inside of the wire to the outside. But there is nowhere for that charge to come from. Charge can't just keep going out without being replaced. So there is something wrong with this picture, and the only thing that can be wrong, because I do know that the current is proportional to electric field, applied electric field, and I do know that I can't have current. So if I take these two facts, it implies the electric field itself is 0. Inside a material which is conducting, if you allow the system to go to steady state, you have to have that the charges settle down in static positions, which means no current, which means no electric field. It is a very standard result. I mean, you learnt it in school, you learnt it in, I am sure, your physics 2, and you are learning it again. And it is not quite true. For example, why can't I have a current that looks like this? Why can't I have a circulating current? I am drawing it with the wrong aspect ratio. Let me draw it more properly. So, it is coming out, going back in and going around, it is cylindrically symmetric, no charge is accumulating anywhere, I do not have to produce charge out of nothing. Why can't it happen? And why can't the current just keep moving? Well, if there is a current like this is a current that is in the direction, and therefore, it implies I have electric field in the theta direction. Let me look from above. So, what will I have? I have my material radius A, and I have current that is flowing around like this. And because of that current, I have electric field that is going around like this. Now, let me choose one point here which I will call A, and one point here which I will call B. Now, you may remember from 2 lectures ago, we proved something. We proved that integral A to B E dot dl was equal to independent of path. No matter how I went from A to B, I got the same answer. So, I can choose 2 different ways. I can choose to go this way, and I can choose to go this way. So, let me label this path C1 and this path C2. So, if I do integral along C1 E dot dl, well, I do not know the answer, but I do know that E is along dl. So, it must be positive. If I go along C2, if I do integral along C2 of E dot dl, well, the electric field is downwards, dl is upwards. So, E dot dl is exactly minus, so it is negative. But it is the same E dot dl, the same E dot dl, one way is positive, one way is negative. There is only one number which is equal to minus of itself, and that is 0. So, you cannot have circulating currents and therefore circulating electric fields inside a material, inside electrostatics. The moment you have Faraday's law, of course, you can have it. And that is a very important topic we will come back to. But in electrostatics, because of this important result, we cannot have any circulating currents, and we cannot have radial currents, because where does the charge come from? Charge can't keep on coming. So, on average the radial currents have to go to 0. So, the result is that inside a material ER goes to 0. So, our plot, this was B, this was A, this was electric field ER, goes to 0 at A and remains 0. The electric field is 0 inside, goes to a value, this value we have worked out already, it has got to do with q over 2 pi r epsilon naught, and then it goes all the way out to B where it drops to 0 again. This is the electric field, and if now in addition I tell you that one of these two, A or B, has a known potential, then in terms of that known potential I can get you the potential as a function of r. Let us see how that works out. Let us say we know phi at A is equal to some V naught. Then phi at any r is equal to minus integral A to r E dot dl. Sorry, phi at plus phi at E. This is only the difference in potential that gives integral A to r E dot dr. But E is radial. So, I can take if I want the potential at any r, I can take a radial line going from A to r. And if I take this radial line, then E dot dl becomes nothing but integral A to r E r dr plus phi of A, which is plus V naught. I already know what E r is. It is equal to minus q over 2 pi epsilon naught integral A to r dr over r plus V naught. This is a very standard integral. The integral dr over r, I say dr prime over r prime up to a limit r is equal to ln r plus constant. Substitute that there, it is equal to V naught minus q over 2 pi epsilon naught ln r over A. Where I have used the property of log, log of r minus log of A is equal to log of r over A. So, you can plot this function on the same plot, and what you will get is a slightly different kind of function. If you plot the log function itself, let me plot it on the same graph as the previous graph. This is A. If you plot log function itself, log of r over A is 0 at r equals A, and it grows very gradually. This function multiplied by something subtracts from the starting voltage. So, if you take that, this is phi, this is the value V naught, you will get a slowly decaying value which is the potential as a function of r. These are important results. They are important because the potential and field between two coaxial cylinders is a very common problem in electrical engineering. It is so common that there are very standard tabulated answers to these geometries. But here I am basically presenting this as a way of understanding how to solve problems using Gauss's law. So, let me review what we have done up to now. We have surface integral E dot ds equals q enclosed over epsilon naught. This is Gauss's law, and we applied it to coaxial cylinders as well as to within a metal, and we came up with solutions for electric field. Now, I would like to go back to the previous formula I had derived. From this, I had given you another formula which was divergence of electric field is equal to rho over epsilon naught. It is the same equation, it is just that since this is true for arbitrary surfaces, it must therefore hold that this equation is also true. Now, let us remember that the electric field itself is got from the potential. This was derived 2 classes ago, so you may have forgotten, but so I will suggest you go back and reread. So, we have 2 equations. We have an equation that relates electric field to charge, and we have a relation that relates electric field to potential. It is very interesting. You start with a scalar field, you create a vector field, take the divergence of the vector field and come back to a scalar field. And what is most interesting of all is that we know, if you know charge density, that is like knowing charges, you can calculate the electric field. So, from potential you can go to electric field, from electric field you can go to charge, from charge you can go to electric field, and we know that if we know electric field we can go to potential. So, this is both ways it is possible to do this calculation. But why go through this electric field at all? This electric field is a complicated thing. I mean, it has 3 different coordinates. We would like to actually go directly from charge to potential. Then we can calculate the electric field anytime we want. How do you do that? Well, I will take the electric field here and substitute this formula. So, let me do that. Divergence of minus gradient of potential is equal to rho over epsilon naught. I can take that minus sign to the right hand side. So, I get divergence of gradient of phi equals minus rho over epsilon naught. Now, this particular form, divergence of gradient, is so common that it has also become a tabulated operator. So far we know gradient and we know divergence. This is called divergence of gradient. It is given a special name, del squared, and is called the Laplacian. Now, the Laplacian is very easy to write down. All we have to do is apply its definition. Divergence of gradient of phi is equal to divergence of unit vector along x del phi del x plus unit vector along y del phi del y plus unit vector along z del phi del z. This is the vector gradient phi. If I take its divergence, what does it mean? It means del x of gradient phi along x plus del y of gradient phi along y plus del z of gradient phi along z. Gradient phi along x is this piece. This is the piece that is along x. So, it is equal to del x of del phi del x plus del y of gradient phi along y, piece multiplying y hat, del phi del y plus del z, the piece multiplying z hat, del phi del z. So, you can see it takes a very simple form, second partial derivative with respect to x plus second partial derivative with respect to y, second partial derivative with respect to z acting on phi. And because of this squared operator, that is why it is denoted as del squared phi. It is a very common operator. In fact, it is probably the most important operator in wave theory. All of physics uses the Laplacian. And this del squared phi is equal to minus rho over epsilon naught. It is a very famous equation and it is called Poisson's equation. Now, why is it so important? I mean, ultimately, if we know charge, if we know rho, we already found out that from rho we can calculate electric field, from electric field we can calculate potential, and we know everything. Why is this shortcut so important? The reason why the shortcut is important is that we do not always know charge. If indeed we knew where charge was, Coulomb's law is all we need. But if you think of electrical engineering, the most important building blocks of electrical circuits, there are three of them: resistors, capacitors and inductors. And one of the three, the capacitor, consists of two plates which are kept at a certain voltage. One plate is kept at, say, ground potential, the other plate is kept at 10 volts. and between those two plates an electric field develops, which is described by Coulomb's law, which is described by Maxwell's equations. So, that is a problem where we do not know rho, we do not know the value of rho. What we know is the potential at the plates. So, let me emphasize this again. We have problems where we actually have that one plate is grounded, the other plate is connected to a battery, and we would like to find out what is happening inside and what is happening on the plate. This requires solving a different problem than Coulomb's law, because we do not know where the charge is. We do not know how much charge there is, we do not know where the charge is. What we know is that the potential here is V naught, the potential here is ground. And it is for solving such problems that Poisson's equation becomes more useful than Coulomb's law. With Coulomb's law you will be stuck, you will not be able to solve this problem at all. But with Poisson's equation you will be able to take this problem and many more complex problems and solve them easily. And this is the major reason why most of electrostatics and this course deals with developing potentials and working out how these potentials interact with each other and solving them. The solution is usually in terms of what are called boundary value problems, because I am specifying the potential at the boundaries and I am asking, tell me what is happening inside.